So now that we have partitioned the world to best of our ability in a given situation, we also go from what used to be deterministic mechanics. So we started saying dynamics is specified by all possible states and by a law that connects them. And now we get a very crude dynamics, but turns out very powerful. These things have names, these regions. So we could call it alphabet, or if you have composite names, you'll call them words or whatever. But basically, there'll be always a bunch of symbols that describe what kind of steps we can take in one time step. That'll be our alphabet. A trajectory in this discretized world will be a sequence, usually bi-infinite sequence, all past and all future of such states. So k's, if you're only looking forward in time, for example, they're just positive integers. If you're looking through all past and future, they're all integers. And these are the sequences of symbols such that the transition from region S labeled Sk, meaning S at time k, one of these letters, to Sk plus 1, the next step, that if this is 1, then we have a description of dynamics, which is called shift dynamics. So instead of thinking originally about particular state space and a particular law of motion that connects regions in continuous or integer time, now we'll describe dynamics as a topological dynamical system, which consists of state space is now all possible shifts. So these are all possible admissible itinerary. And the law of motion is now sigma, which is a shift by one digit in the sequence. And this is what's needed to capture qualitative behavioral dynamical systems, meaning all possible qualitative behaviors. And it'll turn out that it's rather easy to understand, either you're allowed to do something or not allowed to do something, so you keep going in steps, and every step this law tells you what's allowed, and collection of all these possible behaviors, collection of all trajectories. So before we had the spaghetti, we had continuous time trajectory following space. Now we have Poincaré section, discrete time, and we have all allowed orbits, admissible orbits, collecting dynamics. And we'll find very efficient ways of encoding what's admissible, what is not, and we'll be able to make infinite time predictions in a way that will be totally obvious to you. We'll just compute eigenvalues and eigenvectors of transition matrix and understand what that means. This is all easy, and I'll ask you to remember what we got here because you'll think it's a little bit trivial. When we start looking at evolution operators, so what happens when you move densities of probability to state space, we'll do the same calculation, but everything will look much more obscure the moment we do it.